Name the type 2 ionic compound or write the formula. So type 2 ionic compounds are very similar to type 1 ionic compounds in that it's simply the metal name with the nonmetal name with "ide" at the end. However, what does matter in this case is how many electrons is the metal giving away. So if we look at manganese and copper and nickel and vanadium as in these examples, they're all transition metals and they all come from sort of the center of the periodic table. These metals in the center of the periodic table, transition metals, can have multivalent shells, which means that they can sometimes give away 2 electrons, they sometimes give away 3, they can give away 6 sometimes. It's hard to tell, unlike the group 1 and 2, which make up type 1 ionic compounds, which always give away 1 in group 1, always give away 2 in group 2. And so we need to use a Roman numeral in the name to tell us what kind of manganese or what kind of copper we're actually using here. Is it copper 2, which means it gives away 2 electrons, or is it copper 1, which means it gives away 1 electron. And so going from a formula to a name is a little bit tricky in that you have to figure out how many electrons the metal is giving away so that you can include that as a Roman numeral. I want to be clear about this too. The Roman numeral does not mean that you have that many of that element. It means that you have that many. That element is giving away that many electrons. So, for example, C here, nickel 3 fluoride does not mean there's 3 nickels. There might be, but that's nothing to do with the Roman numeral there. The Roman numeral only means how many electrons it's giving away. So, if we look at A, we have manganese and oxygen. So it's going to be manganese something oxide. And I'll leave some space for my Roman numeral here. Oxide. So not much different than type 1. But now we've got to figure out how many electrons it gives away. One way to do that is by looking at the nonmetal here, in this case oxygen. When we look at the oxygen on the periodic table, we see it's in group 16, and that tells us that it needs 2 electrons. So if it needs 2, and there's 2 of them, we have MnO2, that's a total of 4 electrons, which those 2 oxygens must be receiving. And so, since there's only the 1 manganese, we know that it must be manganese 4 oxide. I can draw that visually here. If we have 1 manganese, and we know we have 2 oxygens, and we know that each oxygen, by looking at the periodic table, always takes 2 electrons here, so I'll show those electrons going there. That gives us a total of 1, 2, 3, 4. And since there's only the manganese, which is the only thing that this could be coming from, all 4 of those must come from that 1 manganese, hence the name manganese 4 oxide. We do the same thing for CuCl2. CuCl2, we look at that, we know it's going to be copper something chloride. But how many electrons is that 1 copper giving away? Well, we know that chlorine can only accept 1 electron, and there's 2 of them, so that's a total of 2 electrons coming from that copper, so therefore it must be copper 2 chloride. And so it's always the nonmetal that gives us the clue as to what the Roman numeral is going to be for the metal. You might be tempted to say something like, oh, there's 2 Cls there, so therefore it must be copper 2. That's not always going to be the case. As you can see with the first example, it was manganese 4, not manganese 2 there. But that's a common enough mistake. Going the other way is much easier. When we look at nickel 3 fluoride, we don't need to even look on the periodic table to find nickel at all. We already know that it's got 3 to give away. And we look on the periodic table and we see that fluorine is in group 17, so it can only accept 1. We can use the crisscross rule here, which is simply write out your symbol and how many electrons to give away, write out the symbol of your nonmetal and how many it can accept. We do the crisscross and we get NiF3. So that was a lot easier. You'll see the same thing with vanadium oxide here. Symbol for vanadium is V. The Roman numeral V means 5, and so we have 5 vanadiums, or 5 electrons to give away, I should say, and oxygen still accepts 2. We crisscross that, and the formula for vanadium 5 oxide is V2O5.